We're going to start with the simplest of all the possible parallel computing patterns, which is called map. And the idea is that given an array of input values, you simply apply a function to each value in the input array. So you would have xi at each of the indices going to some function f of xi. And this example is rather trivial, so let's do it in Visual Studio and try to spice it up a little bit. Alright, so let's make a new project. I'm going to put it in here, and I'm going to call it map. Alright, so let me once again get rid of all the scaffolding that's generated here. And let's get rid of this as well. Okay, so we're making a supposedly simple demo which just takes an array and adds, let's say, adds some fixed value to each of the elements, which would be really boring. So let me demonstrate a few more things. First of all, for generating our array of input data, we're not going to just fill it with a sequence, for example. We're going to use a random number generator. And for that, we're going to use one of the libraries that comes with CUDA called cuRAN. So I'm going to hash include cuRAN here. And then what I can do is I can make a random generator. So I can say cuRAN generator t, let's call it gen. Then I need to initialize the generator using cuRAN create generator. So make a generator. And when making a generator, I need to obviously provide value, but I also need to specify the type of the generator that I want to have. And there are many types, but the one I'm going to use is the Mersenne twister. So cuRAN RNG sudo mtgp32, this one. And then I need to provide a seed. So just like in the ordinary C++, I need to specify some seed value for the cuRAN generator. So that's cuRAN set sudo random generator seed for gen, and I'm going to use the current time. So presumably this requires me to have some headers, including ctime. Also add a few more, just in case. iStream, namespace std. There we go. Okay, so we've got a random number generator, and what we need to do is to, well, decide how many values we actually want to initialize. So let's suppose that I want to perform this map operation on 123,456 distinct values. So that's how many values I want to have. Then I would have the size, as always, as count times size of float. In this case, we'll use float. So we need a pointer to the device memory where this is going to be stored, and we also need to actually get the results in an array at the end of it all. So that would be h with count values. Okay, so let's allocate the array d. So once again, CUDA malloc pointer to d and count, no, size rather. Okay, so we've got d initialized, and now we need to generate those random values, and for that we do cuRAN generate control space. You'll see there are different distributions here. I am going to choose uniform, so cuRAN generate uniform, and then I just specify the generator, where to put the values, and how many of them there are. There we go. Notice I'm using count here and not size. That's one of the little things that can trip you up. Now, we've got the generator in place. The next thing we need to do is we need to actually specify the dimensions for our kernel, which doesn't yet exist. And in this case, I'm going to perform a few calculations so that we can sort of figure out how to efficiently use the kernel. So let's suppose that let's start with the thread block. Now let's suppose that I want 512 threads. So I can say that, well, 512 is 8 by 8 by 8. So I can use this dim3 structure that we mentioned. I can say that my block is going to be 8 by 8 by 8, like so. So it's a three-dimensional block. Now remember, I cannot use a three-dimensional grid, so my calculation would go something like this. I know that I have a total of 1, 2, 3, 4, 5, 6 elements, and I divide it by 512 to get 241, which is close enough to 256. So what I would do then is I would say, well, okay, if this is the way it goes, I would make a grid of, let's say, 16 by 16 thread blocks. So 16 by 16 is 256, which is gets me more values than this, but that's okay. That's not a real problem. So now I would fire up my kernel. Let's call my kernel at 10. So I'm going to add the value 10 to each of the random numbers, just so that we can see that it is in fact working as it should. And here I simply specify the grid and the block. There's actually a third parameter that you can add to the kernel call, but we'll look at it later. So what are we going to provide? Well, we're going to provide the input array, which is going to get modified with the adjusted values, and also the count. So because we need to know that the total number of elements that we're going to do this on. And here is where things get interesting. So here's our kernel. Let's make our kernel. This is global void add 10, which is going to take an array D and also the number of elements that we're going to increase. Here we go. Now, we're still going to go with this idea that each element is increased by a separate thread. But now we have a five-dimensional arrangement of threads that we need to process. So how would we get about this? Well, the calculations here, they're actually not as simplistic as you're used to, because we need to calculate the index of an element in a five-dimensional space, and this is something that, well, actually we're going to calculate it in six-dimensional space. So we're going to assume that the grid is three-dimensional as well. So it would look something like this. Let's calculate the number of threads per block that exists. So threads per block, and this is simply a multiplication of all the block dimensions. So blockdim.x times blockdim.y times blockdim.z, like so. Let me get rid of this for a sec. Okay, so threads per block. The next thing we need to do is figure out the position of the current thread in a block. And this is going to be a bit ugly. So thread position in block equals, so that's thread index.x plus block dimension.x times thread index.y plus block dimension.x times block dimension.y times thread index.z. As you can see, it's rather convoluted, but that's how you do it in 3 dimensions. And we have to do pretty much the same thing in the calculation of the block position in a grid. So block position in a grid is block index.x plus grid dimension. Actually, we can pretty much copy this. We can copy this calculation because it's a similar 3-dimensional calculation, but we need to do some replacement here. So we need to change block to grid, replace all, and then we need to change thread to block. There we go. All right, so that's block position in a grid, and now we put it all together. So the final thread ID is block position in a grid times threads per block plus thread position in the block. And now with this TID, we do a very simple manipulation. So we say that if the thread ID is less than count, then we say that d at this thread ID equals d at this thread ID plus 10. Simple as that. All right, so let's get back to the main method and finish it off. So we have the calculation, the kernel that's going to execute, and now what we're going to do is we're going to copy the values back to H so we can look at them. So that's done with CUDA memcpy with the copy to H from the size and CUDA memcpy device to host. There we go. And then don't forget you have to CUDA free the pointer to device memory, and then we can print just a few of those values. Let's say the first 100 plus plus I. Let's see out H at I and line. I'll put a get char here at the end. Here we go. Okay, so we can run this. All right, so we're seeing an error that for some reason we cannot use this currand function. And in fact, even though we included the header, we forgot to include the library reference. So let's go into project properties and actually fix this. So if you go into project properties and you go into linker and then input, you'll see that some libraries are being included here. So let's go into all configurations and then just edit this, and you'll see a dialog like this, and just add currand.lib. There we go. All right, so let's try again. And here are the values. So as you can see, it worked amazingly enough.